Hello and welcome to a new chapter. In this chapter, we will be discussing about electrical signals in general, about their properties and many more. In this particular course, we begin by looking at AC signals and its properties. After that, we will talk about DC signals and we will see briefly how to convert AC signal to DC. After that, we will look at some interesting type of signals like ramp and triangle. And last but not least, we will talk a little bit about noise, not the type of noise that you hear on the street, but the electrical noise that is causing a lot of headache to engineers. So, let's get started. So, as I said, we will begin with AC signals. AC comes from alternating current while DC comes from direct current. Even though AC comes from alternating current, in the world of electrical engineering, when we say AC, we are more inclined to refer to the voltage of the signal rather than the current. So for example, here we have a 12 volts AC power supply, which outputs a 12 volts AC voltage, and if the voltage is alternating, then the current will implicitly alternate too. It's not possible to have an AC voltage with DC current, for example, because the voltage is the one that causes electrons to flow, and current always follows the voltage. So AC voltage means an AC current as well. Alright, here we are. So in this circuit we have an AC signal generator and a resistor to avoid creating a short circuit, in other words, to limit the current. Let's have a closer look at this AC voltage. So as you can see here, alternating current flows one way, then the other way, continually reversing direction. If I stop the simulator, we can notice that the AC voltage is continually changing between positive and negative. How many times the wave is passing the 0 point in a certain amount of time is called as frequency. In other words, the frequency is simply how many times per second the wave oscillates. We normally use a time for 1 second, so this gives a frequency the unit hertz, since 1 hertz is equal to 1 wave per second. 1 wave per second means that the wave needs 1 second to go from this point until this point. This is what we call a single cycle, which comprises of 1 positive swing plus 1 negative swing. Why don't we take another example to understand this frequency better? So we have 3 identical circuits. The only difference is the frequency of the signal that our AC source outputs. The first AC source outputs a signal of 40 Hz, the next one outputs a signal of 80 Hz, and the last one 160 Hz. Now notice the difference between each signal. Do you see any difference? The lower the frequency of the signal, the more time it needs to make an oscillation of 1 positive swing and 1 negative swing. The higher the frequency, the faster the signal oscillates in 1 second. Alright, so an AC voltage is continually changing between positive and negative, right? The rate of changing direction is called the frequency of the AC, and it is measured in hertz, which is the number of forwards, backwards cycles per second. Now let's check some of the most important properties of an AC signal. This voltage time graph shows various properties of an electrical signal. In addition to the properties labeled on the graph, there is frequency, which is the number of cycles per second. So this diagram shows a sine wave, but the properties apply to any signal with a constantly repeating shape. The first property of an AC signal is its amplitude, which is the maximum voltage reached by a signal. I guess you know the amplitude of the voltage is measured in volts. Many people confuse peak voltage with the amplitude of the voltage. Peak voltage is just another name of amplitude. On the other hand, when we say peak-to-peak voltage, that's totally different. Peak-to-peak voltage is twice the peak voltage of our amplitude. For example, when reading an oscilloscope trace, it is usual to measure peak-to-peak voltage. We can see that from this point to this point, it's called as time period. Time period is the time taken for the signal to complete 1 cycle. It is measured in seconds, but time periods tend to be shorter as milliseconds, microseconds, depending on the frequency of the signal. Depending on the frequency of the signal. This means that time period and frequency are closely related to each other. Let's think about it. If the time period increases, the frequency increases or decreases. Exactly, it decreases because it needs more time to complete one cycle. So we can say that frequency is inversely proportional with the time period, and the equation of frequency is the following. So frequency is the inverse of the time period, while time period is the inverse of frequency. I hope it makes sense. So let's define the frequency to have this written down as well. Frequency is the time taken for the signal to complete one cycle. It is measured in hertz, but frequencies tend to be high as kilohertz, megahertz are often used. For example, the main electricity coming from a wall plug in the UK has a frequency of 50 Hz. An AC supply is suitable for powering some devices such as lamps and heaters, but almost all electronic circuits require a steady DC supply. And this brings us to the next topic, which is DC signal. So direct current or DC flows in the same direction. It doesn't reverse directions like AC voltage, and the DC voltage of course can be higher or lower, and this voltage is always positive or always negative depending how you look at it. Electronic circuits normally require a steady DC supply which is constant to one value, or a smooth DC supply which has only a small variations called ripple. For example, cells, batteries, and regulated power supplies provide a steady DC which is ideal for electronic circuits. If you have a mobile phone, you have as well a charger to it, right? But how does a charger works? What components does it have inside so that it takes a high voltage AC signal from the wall plug and converts the voltage into a clean 5 volts DC signal? There are a few steps involved in order to convert AC to DC, something that we will learn in more details in the future, and explaining how to do it would go beyond the scope of this course. But briefly, this schematic shows how to convert AC to DC. Instead of talking and explaining how about this schematic, I built this one in the simulator, so let's go there. In order to produce 5 volts output, it needs input voltage. That input voltage is usually 220 volts AC, and that is common domestic value being used in home, in Europe at least. So 220 volts is too high, right? And in order to transform this high voltage into a smaller one, we use a transformer. A transformer looks like this, and it has 3 important components. One is the magnetic core, primary winding, and secondary winding. The primary winding is the part that is connected to the input AC voltage, and the lower AC voltage is taken from the secondary winding. Since the secondary winding has less windings or coils than the primary winding, the output voltage will be less than the input voltage, and this is what we call a step-down transformer. So this is the first step, and the next step is the process which converts AC voltage to DC. But conversion will not be 100% done. There will be an incompleteness in conversion, meaning that it will have huge ripples, as you can see here. And if we want to get rid of this ripple, we need to use a filter capacitor that will lower these high ripples to a moderate one, which is acceptable by many devices. By adding a filter capacitor, you can see that we managed to decrease those high ripples to a moderate one, which is acceptable to many devices. The final component is the load, in other words, the beneficiary of the total process. 5 volts output is consumed by the charger in order to carry over electrons inside the smartphone to fill up battery energy. Alright, the next signal we are going to talk about is called as ramp. The ramp is a signal that looks like here. It is simply a voltage rising or falling at a constant rate. That can go forever, of course, even in science fiction movies. It is sometimes approximated by a finite ramp or by a periodic ramp, also known as sawtooth. It's called a sawtooth because the waveform resembles to the teeth of a plain-toothed saw. Triangle. The triangle wave is a close cousin of the ramp. It is simply a symmetrical ramp. Note that just like an AC sine wave, triangle wave reverses direction periodically. So it changes between positive and negative, which makes triangle an AC signal. The last waveform we will talk about is called as noise. Well, in daily life we have the weather to serve as a universal means of starting and maintaining conversations. In the electronics world, noise can play a similar role, in the sense that it's always present and always is causing some sort of problem. If a design review meeting, for example, is slowing down but no one is willing to relinquish the conference room just yet, all you need to do is mention the N word and the discussion should be lively for at least the next half an hour. If your newest PCB is working fantastically well but you don't want to sound overconfident when someone comes and asks you about it, just complain about the noise. If your PCB is failing miserably and you are not sure why, blame it on noise, which is always guilty until proven innocent. Alright, but what is noise? Well, this question is somewhat difficult to answer if you try to go really deep, because you end up in the philosophical realm confronting issues like why is life so complicated, or why can total entropy just decrease over once in a while. But if you are satisfied with a more superficial treatment of the topic, electrical noise is straightforward. Noise is a generic word that refers to variations in voltage or current that are often random, usually of relatively low amplitude and always undesirable. So if you ask where does noise come from, well, noise can come from anywhere, like from the air, the power supply, switching regulators, resistors, transistors, etc. Going deep into explaining why is noise generated is a complex topic, and explaining it would go again beyond the scope of this lecture. So we will finish the course here, and thank you for watching and see you next course.